Hello again. This is Math 2231 coming to you from the College DePage, and the title of this lecture is Pondering Infinity, Part 2, as we study limits. As always, please be an attentive learner while watching this video. By way of introduction, thus far we have studied limits that look like this. The limit as x tends to c of f of x equal L for both c and L being real numbers. Now today, in this video, we're going to discuss what it means to broaden these concepts for both of these variables. We have already considered letting L be infinitely large in part 1, and now we're going to consider allowing C to grow infinitely large. And the terminology is, this is the limit at infinity. So we're going to be discussing the end behavior of a function on an infinite interval. So to start out with, consider the graph of y equals f of x equal 3x squared over x squared plus 1. And the picture of it is shown in the picture down here. And graphically, down here, you can see that f of x appears to approach 3 as x goes without bound, either in the positive direction or in the negative direction. Again, x is the thing that is increasing here. You can come to the same conclusions numerically as shown in the table. So here what we're doing is we're picking values of x that are bigger and bigger and bigger, and smaller and smaller and smaller, larger in absolute value in the negative sense. And in both cases, you can see the numbers get closer and closer to 3. Now the table suggests that f approaches 3 as x increases without bound, x tends to infinity. And similarly, f of x approaches 3 as x decreases without bound, as x tends to minus infinity. These limits at infinity are denoted by, and we will write it this way, the limit as x tends to infinity of f of x equal 3. Actually, that's minus infinity up here. So that's the limit at minus infinity or at negative infinity. And the limit as x tends to infinity. Notice we don't write the plus sign all the time. We can write it or not write it, is equal to 3. And that's the limit at positive infinity. Now, so the statement, the limit as x tends to minus f of x equal L, or the limit as x tends to infinity of f of x equal L, means that the limit exists and the limit is equal to L. Now to say that a statement is true as x increases without bounds means that for some large real number m, in fact any real number m, this can be true, but we're going to be talking about the statement, we're going to be picking any m, but the statement must be true for all x in the interval where x is greater than m. So anyway, here's the formal definition of a limit at infinity. Let L be a real number. The statement, the limit as x tends to infinity of f of x equal L, means that for any epsilon greater than 0, there exists an m greater than 0, such that whenever you're bigger than m, the absolute value of f of x minus L is less than epsilon. Note the absolute value is here again. And similarly, the statement the limit as x tends to minus infinity equals L means that for each epsilon greater than 0, any one you pick, there exists an n less than 0, such that whenever x is less than n, that means the absolute value of x is greater than n. The absolute value of f of x minus L is less than epsilon. Please ponder these until you understand them. The definition of a limit at infinity then is shown even in this figure. So you see we pick an epsilon greater than 0, so we go up here to L plus epsilon and down here to L minus epsilon. But then there's a positive number m, and we have to find m. It can depend on epsilon, such that m, whenever we're bigger than m, even though you see there's some wiggling here, the functional values, the y, stay within epsilon of L. And again, f of x is within epsilon units of L as x goes to infinity. And you might remember that back in your pre-calculus, you called these horizontal asymptotes. And so the line y equal L is a horizontal asymptote, and here's the official definition in terms of limits. The line y equal L is a horizontal asymptote of the graph of f when the limit as x tends to minus infinity of fx equal L, or the limit as x tends to infinity of f of x equal L. Now please understand from this definition that the graph of a function can have at most two horizontal asymptotes, one to the left, and it perhaps could be a different one to the right. Not always, but it could be a different one. Limits at infinity have many of the same properties of limits that we've discussed before. For example, the limit as x tends to infinity of the sum of f and g is the sum of the limits. And the limit as x tends to f and g, as x tends to infinity of the product is the product of the limits. And again, we're assuming that all these limits exist. And similar properties hold for minus infinity. So when evaluating limits at infinity, this theorem is useful, and this is a theorem that you should understand the results, because we're going to be applying it a lot, and I think we'll talk a little bit about even the proof of this. So this is limits at infinity. If r is a positive rational number and c is any real number, then the limit as x tends to infinity of c over x to the r is equal to 0. Now you see there's no x in the denominator, and our conditions on this exponent means that this is going to get bigger and bigger and bigger in the denominator. This is going to be denominator heavy, and since you're bounded by c in the top, eventually the denominator is going to get this very close to 0 as x gets large. Furthermore, if x to the r is defined when x is less than 0, and that really depends on what r is, because you can be taking square roots of numbers. But if they're positive, it's defined, then that is also true that the limit as x tends to infinity of c over x to the r is equal to 0. So if we're bottom heavy, we go to 0. And let's look at the proof of this. Okay, so we want to show that the limit as x tends to infinity of, and we're just going to start with being 1 over x, and then we certainly could multiply by c, and c times 0 would still be 0, so it is really pretty much sufficient to prove this. So let's take epsilon greater than 0, and let's let m be 1 over epsilon. So if x is bigger than m, then x is bigger than m equal 1 over epsilon. But that implies, if we solve this, that 1 over x is less than epsilon. And that means that if the absolute value of 1 over x minus 0, which is what we have here, is less than epsilon. So by the definition of limit at infinity, you conclude the limit as this limit of 1 over x as x tends to infinity is 0. Now using this result and letting r equal m over n, what we can do is, first of all, we can pull the c out, and we can use the continuity of the function. This one goes to 0, and so that whole thing is also equal to 0. And the second part, the proof of the second part of the theorem would be similar. For the most part, you're not going to be proving this theorem, you're going to be using it. In fact, let's use it right now, or use some of these theorems to find the limit at infinity for the limit as x goes to infinity of 5 minus 2 over x squared. Well, you see, we're going to be taking the difference of the limit, so the limit as x goes to infinity of 5 is just going to be 5. But then when we take the limit, so that's going to be minus the limit as x goes to infinity of 2 over x squared. But 2 over x squared is going to be equal to 0. So what we see is that this limit is just going to be 5. And here you can see that y equal 5 is a horizontal asymptote if we look at the graph. And I think that's all we need to say about this. Let's do another problem though. We want to find the limit as x goes to infinity of 2x minus 1 over x plus 2. Now, if you look at the top and the bottom, and this is kind of thinking about, well, what happens if you just see what happens to the top and what happens to the bottom, you see that they both go to infinity. And infinity over infinity is another indeterminate form. It's like 0 over 0. We don't know what it is. So to resolve this problem, what we're going to do is use the technique. I talked about this in the classroom lecture the other day. What we're going to do is we're going to divide both numerator and denominator by the same thing, x. And so when I do that, and I take x into each term in the numerator, I get 2 minus 1 over x. When I divide x into each term in the denominator, it is 1 plus 1 over x. And you see these last two terms go to 0 as x gets large, and so the answer to this theorem, or the answer to this question is this limit is going to be 2. And in fact, here you can see a graph of that, and you see that we do have a horizontal asymptote. And note that in this problem we also have a vertical asymptote. When you encounter an indeterminate form, such as the one in example 2, and this is the generalizable result, you should divide the numerator and the denominator by the highest power of x in the denominator. So y equal 2 is a horizontal asymptote to the right, and it's also the horizontal asymptote to the left. And this is the graph of the function. I already mentioned that, yes, you have vertical asymptotes here as well. Here are 3 problems that you really should think about, but they're all different. You see, in the first one, this is bottom heavy because I have an x cubed in the denominator. So if that is an x squared. So if I divide top and bottom by x squared, this is what I get. And so you see the top, each of those becomes 0, so it's 0 over 3, and so this one goes to 0. Now here you have the degree of the numerator is 2 and the degree of the denominator is 2. So when I divide by x squared, top and bottom, I get that this goes to 2 over 3. And the last one, we have x cubed over x squared, and when I divide top and bottom, I get that it is like 2x, and that is going to go to infinity. So you see, if the leading coefficients, the highest degree terms, are if the numerator and denominator are of the same degree, when I divide, it will go to the ratio of the leading coefficients. If it is bottom heavy, it will go to 0. If it is top heavy, it will go to infinity. Now, when you go to infinity, sometimes the book will say that does not exist because limits have to have real numbers, but we also define what it means for a limit to be infinity, and so I would expect my students to say this limit is equal to infinity when it increases without bound. Okay, so this sort of summarizes the discussion that we've had thus far about this. If the degree of the numerator is less than the degree of the denominator, the limit will be 0. If the degree of the numerator is greater than the degree of the denominator, it goes to infinity, and the limit does not exist as a real number. And if the degree of the numerator is equal to the degree of the numerator, then the limit of the rational function is the ratio of the leading coefficients. Okay, so you can apply that, for example, to this function 1 over x squared plus 1, and you realize, oh yeah, this goes to 0, and it's almost a bell-shaped curve. And so you have a horizontal asymptote here at y equal to 0. We did say that a function could have 2 horizontal asymptotes, and here is a here's some discussion of having two horizontal asymptotes. And this is similar to what I talked about in class. Let's talk about this first one. The limit as x goes to infinity of 3x minus 2 all over the square root of 2x squared plus 1. Now the square root of 2x squared plus 1, you can divide top and bottom by x. And again, we're going to positive infinity. So that means x is positive. So dividing by x and dividing by the square root of x squared, which is the absolute value of x down here, can happen. So if we do that algebra, we will get a numerator of, and we will cancel the common factors, we'll get a numerator of 3 minus 2 over x, and a denominator of the square root of 2 plus 1 over x squared. So 2 over x goes to 0, and 1 over x squared goes to 0. So the answer to this problem would be 3 over the square root of 2. Now, if x is less than 0, the square root of the absolute value of x will be the square root of x squared. And you see that x is going to be negative. And so what will happen is you will have 3 minus 2 over x. But down here you will have a negative because you're going to minus infinity. And so the answer here is minus 3 over the square root of 2. So you see we have a horizontal asymptote up here if we're going to the right, and we have a different one going down here. We can also talk about limits involving trigonometric functions. We could talk about what is the limit as x goes to infinity of the function y equals f of x equal sine x. But sine x, as you know, goes up and down between 0 and 1, or excuse me, between minus 1 and 1. So it just keeps doing that forever and ever and ever. So you see you never get close to and stay close to a function, to a number, I guess I want to say. And what that means is that the limit doesn't exist. But in part B, if we say what is the limit as x tends to 0 of sine x over x, you do have this wiggling, but you see since the sine of x is between minus 1 and 1, this forms an upper envelope for the function. This forms a lower envelope for the function, so it starts wiggling back and forth, but closer and closer to 0. Now, we can see that, in fact, and I'm just going to summarize the solution to part A. As x approaches infinity, the sine function oscillates between 1 and minus 1. The limit does not exist. Now, part B, though, what we can say is because sine of x is bigger than or equal to minus 1 and less than or equal to 1, it follows that for x greater than 0, you say that, okay, I can just divide all the way through here by x, and the sense of the inequalities is maintained, and so I have that. But the limit on this side is equal to 0, and the limit on this side is also equal to 0. That means the limit of this exists, and it's equal to 0 by the sandwich theorem, or the squeeze theorem, I guess we call it in this course. Finally, there are practical applications where we really do look at the limiting process. Here, without going into details of the discussion, you have a pollutant that has been injected into a pond, let's say, and so the oxygen level really tanks. It goes way down here to about 50%, and so this is a toxic environment. Fish are not living, and so on and so forth. But if you let nature be alone and don't put any more toxins in, nature will correct it, and eventually we'll get closer and closer to being oxygenated. So the level of oxygen in a pond approaches the normal level of 1 as t approaches infinity. Now we're going to have one more segment in this presentation. So far we've discussed that for L being infinity, we've talked about what happens as c goes to plus or minus infinity. And now we're going to allow both L and C to grow infinitely large. So we'll talk about what does it mean to have infinite limits at infinity. And so here's the definition of infinite limits at infinity. Let f be a function defined on the interval from a to infinity. The statement the limit as x tends to infinity of f of x equals infinity means that for each positive number m, there's a corresponding number n greater than 0 such that f of x is greater than m whenever x is greater than n. And the statement, the limit as x tends to minus infinity of f of x, the limit as x tends to infinity of f of x equal minus infinity means that for each negative number m, there corresponds another number n such that whenever an absolute value of x is greater than n, that forces f to be less than m. Okay, and so this is the limit as x tends to infinity f of x equal minus n. Now similar definitions can be used if you switch things with minus infinity. So determining whether a function has infinite limits at infinity is useful in analyzing the end behavior of its graph. And we will do some more of this when we do our chapter on curve sketching. And so we see that this is the graph of y equals x cubed, and as x gets bigger and bigger and bigger, you see that y is getting bigger and bigger and bigger, and likewise as x goes to negative infinity, this goes down. So you see here is an example of having infinite limits at infinity. And here is a problem where you're trying to you're seeing these limits, but also what you see that both of these are top heavy. So you see this one, if you divide top and bottom by x, you see that this line looks like 2x minus 6 and then something that goes to 0. So you see this dotted line is 2x minus 6, but it does go up to infinity as x approaches infinity. Similarly, whenever you divide by x, when you're going to minus infinity, you still have the same oblique asymptote, and sometimes this is called a slant asymptote. Now, one more remark I want to make is there is a limit that's very worth mentioning here. Consider the limit as n goes to infinity of 1 plus 1 over n whole to the n. Now, for any value of n, 1 plus 1 over n is bigger than 1. And so if you take any number bigger than 1 and you raise it to the nth power, like 2 to the n, it will go off to infinity. Similarly, because it's bigger than 1. But the other thing that we could say is, yes, but in here, if you're taking values of n, this gets really close to 1, and 1 to the n, the limit as n goes to infinity of 1 to the n just would be 1. So you kind of say, boy, I don't even know if this limit exists, because I can kind of make arguments for it being infinite, and I can make another argument for it being 1. Well, it turns out that the easiest way to do this right now is just for us to pick values for n. And you see I pick increasingly values. This is an enormous value down here. This is 1 times 10 to the 11th power. And then I'm plugging it in, and I'm seeing what do we get for this expression, 1 plus 1 over n to the n. And you notice that, oh, gee, it actually does converge and seems to be 2.71828, and so on and so forth. And this is true. This limit, which is a little bit surprising, does exist, and it's equal to the irrational number called e. And later on in this course, we need a little bit more calculus machinery before we can do this, but we will provide an analytical proof of this fact later in this course. A very important limit. In fact, some people argue that e is the most important number of all the numbers. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. God bless you all.